Hello, everybody. Yes, we were in the multiple linear regression, and last time we talked about classical criterions for optimal estimators. So that if we want to choose an estimator, that it would be a good choice to have a so-called unbiased estimator, so that we do not make in general an error because the expected value of our estimator should be the true value itself. The second one was efficiency, that we also want to choose an estimator which has not a large dispersion, or at best that it has even the smallest variance out of all unbiased estimators. Then we call this an efficient estimator. And the last one, the last criterion was sufficiency. This I, yes, had here. And sufficiency, I explained to you that this should mean that we want to use only the relevant information. And having these properties, then we can ask within our multiple linear regression, what would be a good estimator for the error which we have in the multiple regression. And remember, when we have introduced an estimator for the variance in general, we have introduced that an estimator for the variance would be the sum over all errors now divided by n minus 1, where we then could show that this is in general unbiased. And if we now switch to the multiple linear regression, then unfortunately we see that even this estimator would still be biased, but that then, since we have now more regression parameters, we can in generally similar like for this estimator, we can show that if we do not divide by n minus 1 but by n minus k plus 1 times the sum of all squared distances with respect to the arithmetic mean, then this means that we have an unbiased estimator where k plus 1 is just the number of all our regression parameters. And then you see, well, if we have only one regression parameter, then of course this number would be just 1, which we have here if k plus 1 equals 1, and this is then also called the number of degrees of freedom in our system. Well, and now we want to ask what would be our errors in our case when we have this multiple linear regression. And for this, we can then move into our derivation for the betas of our multilinear regression. And since we have assumed that, where did we had it here, that all single errors should have the same variance, we can take out this variance just multiplied by this inverse of xt times x. Remember, we had derived this from our calculation of the error via this matrix multiplication. And then we can define from this for our errors that this is just more or less the diagonal elements of these inverse matrix, and then we obtain by taking the root just that the errors of all single estimators are the standard deviation, where we assumed that this is constant for all parameters, times the square root of the diagonal elements of our inverse matrix. And remember, although it is quite hard to calculate such an inverse matrix, in general we have the data and then we just can calculate it, and this are doing right now, of course, the computers for us. And then also additionally, if we take all our assumptions about the multiple linear regression which we have made, that then we also can show that our estimators are normally distributed, just with an expected value of beta I and this variance sigma hat square times the individual diagonal elements. Okay, and for what does we this need? Well, we want to come to answer not only from a descriptive point of view, but given some error probability, we want to talk about the question, how good is our fit of our data? And this is in general the doing the hypothesis tests. And for this, in general, we say, well, we have some data set, and using our data, of course, it could be that we obtain out of our survey data a wrong estimate for the overall set which we have. And for this, then we make the assumption that our hypothesis that we have a good estimate is okay. How large would be the probability that this assumption, this hypothesis is wrong? And this I can explain at a little example. Think, for example, that you have a company and you think of doing a new marketing concept to implement this. And up to this, you know from history that roughly the awareness of your product is 40% out of the population, out of the consumers. And then you make your marketing activity. And after that, you are asking 1,000 people, again, maybe out of all possible consumers in Wilhelmshaven, 80,000 people, you ask 1,000. And after your marketing activity, you get the answer that 420 people answering now that they are knowing your product. And of course, 420 divided by 1000 is 42%, which is larger than 40%. Well, now from a descriptive point of view, you could then make the argument, well, the awareness has increased because now 42% of the people are knowing my product. But of course, you have only asked 1,000 people, and maybe by accident, you have in general asked, so to speak, the right people. Maybe many people which have already known your product also without this marketing activity. And so until now, with our descriptive analysis, we can also only say, well, out of this survey data, well, there are 42%, but from this we cannot conclude that overall my marketing concept was a success. And for this now I make the assumption, for example, well, the awareness of my product has increased. This is my hypothesis. And now it can be possible that I only have asked the right people. This I don't know. And therefore, it can even be the case that if I would have asked all people, all 80,000 consumers, possible consumers, that even the awareness has decreased. So maybe my assumption that the awareness has increased is wrong. And for this, I choose then a confidence level for which my hypothesis is still true, or on the other hand, just an error probability. So I then set this error probability, for example, to 5%. And then I said, well, can I rely on my data asking these 1,000 people with an error of 5%, that my assumption that the awareness has increased is still true. And of course, this hypothesis testing, this I can make in such a way that I just state the hypothesis which I want to test and the contradiction. And the first one I call null hypothesis, and the alternative, this is just the contradiction. And what I stated in this example was that I said, well, the awareness has increased, so then H0 would be my estimator is larger than my starting point, some constant in general C, or the other way around. I can also make the hypothesis it has decreased, then it would be less than C. Or in general, what is also quite often done is that I just make the assumption, well, my awareness in my example has changed or not. And this then would mean H0 is nothing has changed. And since I'm going once to the left, once to the right, and here, so to speak, to both sides, I call this a left-sided, a right-sided, or a two-sided test. So the first step would be then, well, what would be a reasonable hypothesis? And then, of course, I can have, so to speak, two kinds of error. The first error, which I almost always choose, is the error of first kind. So it could be the case that I'm rejecting the null hypothesis, although it is true. Remember, I'm only asking 1,000 people out of 80,000 people. Or it can be also the other way around, and this we call the beta error, or the error of the second kind, is that I'm not rejecting the null hypothesis out of my data, although it is not true. And as I said, mostly the error of first kind is chosen, and quite often it is just said that the alpha is 5%, but actually this alpha equals 5% just comes from the, so to speak, inventor of this decision concept, Mr. Fisher, in the beginning of the 20th century. And he said, well, in general, we can reasonably choose alpha to 5%, but still you have actually, for every experiment you are doing, you have to choose the right alpha. And this error probability is then the error of first kind. So the probability that I'm rejecting H0, although it is true. So I want a statement that, so to speak, I can say, well, I only make an error with 1% if I set alpha to 1%, or 5% if I set it to 5%. And what we quite often see is that in general we ask for error probabilities of 1, 5, or 10, or sometimes also in other experiment of 0.1%. Well, and this more or less we held already, that yeah, we have this left, right, and two-sided tests if our critical value or our test statistic later on in the multiple linear regression, this will be our estimated beta factors, that they are larger or less, or that they are just equal to our critical value. This was at the other slide just our value C. And of course, that we later on can make our calculation, we have to make an assumption: how are my variables distributed? Quite often we choose, or there are reasonable arguments that my variable is normally distributed, but this has not to be in general the case. And in our example with the multiple linear regression, we will then see that there our estimation parameters are not normally distributed, but that they are following some other distribution. But let us go at first to the maybe starting point, that in general you have some survey data, and the first thing which we are doing is in general that we are just calculating the mean. And maybe let's assume a normal distribution. And then we have our density function, and we are calculating then our mean. This would be our mu. And let's say that our parameter is symmetrically around 0 distributed. And think again, well, I have asked my 1,000 people out of my survey data, and then I have my critical value. And if my estimator is then found on the left or the other way on the right, this is then the area where I reject my hypothesis. And this is then, for example, the area here is, oops, 5%. So the overall probability should be 5%. And in case if we have the two-sided test, so these are the one-sided, and this would be then the two-sided, also with an error probability of 5%, then of course both areas together have to sum up to our overall probability. So these two areas, these areas has to add up to the error probability of alpha, for example, 5%. And on the other way around, this overall probability would be then, 95%. Okay, and now we are going to our multiple linear regression. And for this, we are calculating two test statistics. One statistic, the so-called F-test, is calculated more or less on the question, do we have a correlation or do we have not a correlation? So we are testing for, is our R squared, our coefficient of determination, 0 or does it differ from 0? And then of course we want to test for our parameters, and this is the so-called t-value. And the t-value is just defined. Let's start with this. That we have our parameter beta hat, which we have calculated from our multiple linear regression. We have a corresponding error, which we have calculated. Remember, sigma hat times the square root of the diagonal elements of the inverse of x tx. So these two values are calculated from the data. And then we have an idea, maybe that we assume, well, our true beta should be maybe, for example, 1. And then we subtract our hypothesis critical value from our estimated value from our data. And for this test statistic, we can show that this is following the t distribution. And how this t distribution looks like, I will show you in a minute. And for a test in general, do we have a correlation or do we not have the correlation? For this, we calculate an so-called F value, where we find here our coefficient of determination, the residuum, so 100% minus our coefficient of determination, and divided, so to speak, with our number of freedoms, how much regression parameters we have. So here k plus 1 is again the number of regression parameters, and n is the number of the data points. So if our sample has a size of 100 and we are fitting, as we have done in our example, for 3 parameters, then we have 100 minus our 3 minus 1, so 100 minus 4. And we find this number also in our t-distribution. Yeah, and with this test statistics, we then can go to our hypothesis testing, and in general we ask also, using our t-test, that we set our assumption values for beta, the critical values, just to 0. So we ask, can we rely that we have, if beta is a positive dependence between my variable and the outcome. So then how would then look like our F-test? Well, we are formulating our null hypothesis. And our null hypothesis is just that we assume, although maybe the outcome of our data, of our survey data, says there is some dependence, that we just assume, well, there is no correlation. What does this mean that we have no correlation? Well, this we can translate in two conditions. The one would be that we have, so to speak, in the two-dimensional case, only just a horizontal line. Or in general, if we make here our multiple linear regression, that all our beta values are just zero. But this, of course, then also translates into the assumption that the coefficient of determination is just zero. And then the alternative can be also formulated in two ways. The one is, of course, okay, r squared is different from zero. There is a correlation, or, and here you have to be a little bit careful, not all betas, but only one beta just differs from zero. This is just the alternative. Well, and then of course we have to choose our error probability. As I said, general standard significance levels are 10, 5, 1 or 0.5. But of course you have to be careful that this error probability really is reasonable for your experiment. And then we are calculating our F statistic due to this formula. And then we look, well, how does such an F distribution looks like, and if we are then in the right or left part due to our density function. And this, let's choose now somehow our example which we had in where we have calculated the empirical values. This we will do just in a minute. Remember, let's go into our example. Are we? Here. Let's maybe also copy this and just go to Excel. And that I have a little bit more. Let's choose 3. This should be enough. Yeah. Or visits, marketing, branch, sales. So we have 1, 2, 3. This are our betas. And up here we are. So we have 3 betas. This means k equals to 3. We have 8 data points. Let's put this here. 1. So 8 minus 3 minus 1 is just 4. So we have an F distribution depending on 2 parameters with 3 and 4. And this F distribution is not symmetrical like the normal distribution, but in general it has such a shape. And if we now want to test for a level of 10%, then we have to calculate, oops, the, so to speak, theoretical value. How large has our F value to be if, or that this area is 90%. And this then would mean if our estimated value for F would be smaller than this critical value, then our assumption that there is no correlation would be not rejected. And if we are on the right side, then it will be rejected. Well, let us directly switch to very horrible formulas, because then it can be shown that this F distribution, distribution looks like this, and there it is, depending on our two parameters, that it has in general this asymmetric shape. And well, it always differs if our k and n is differing, and therefore we find for such a distribution, which is itself depending on parameters, we find tables for these distributions. And then df1 and df2 are our two parameters. So this would be then n minus k minus 1, and this would be k. And since we have k is 3, we are just here. And n minus k minus 1 is 8 minus 3 minus 1 is 4. And then we find that this theoretical value would be just 5.34. And now comparing this 5.34 with our number coming out of the data, then we can decide if we can reject if we find this value in this area, or on the left, then we do not reject our values. Well, and for all these values, of course, we have to do our linear regression. Then we have to calculate this. Where did I had it? This may be horrible inverse matrix, but this, of course, fortunately can be done just using some standard software package. And well, there are add-ins for the multiple linear regression for Excel. This you can download, but what we also can do is In general, it is implemented as RGP. Given our data, this just calculates for us the multiple linear regression, all these inversion of this matrix. So then, of course, here we see we have at first to feed in our y values and then our x values. And later on we have also to add that we want to have our constants and that they are it is given our output statistics. Therefore we have to add true in English 2 times and pressing enter, and this data which we get here is let me move this down. This I already copied for you that you can see this. That then we directly obtain the values for our beta estimators. So minus 2.99 for beta 3, beta 2, beta 1, and the so-called cut of the vertical axis. These down here are then more or less our diagonal elements. Standard error of beta 3, beta 2, beta 1, and beta 0. And here we obtain what we need for the f-test. We also directly obtain our r squared. So from a descriptive standpoint, we can say that our data says that we can explain almost 72% with our linear model. But now with the hypothesis testing, we want even to answer the question, not only from a descriptive standpoint, but also given some error probability, in our case now 10%, can we, for an error probability of 10%, say that we can rely on our data that there is a correlation. So let's then roughly say r squared is 0.72, and for this we have to calculate our f value. And let me also show you, giving here also the link. There you can find the description of the RGP function in Excel. Let me put this just let's put this here. Okay, and down here, and that is active. Then you can later on just click on that. Okay, so using this software package, we have obtained an r squared of 0.72. And here we have our f value. Let's copy this one also here. And now we have just to put in our data. So we have done 0.72 divided by k, 3 estimating parameters divided by 3, 1 minus 0.72 divided by number of our data points, 8 minus 3 minus 1 is then divided by 4, and this I've done for you already is roughly 3.42. Well, and now if we compare this 3.12, this would be then somewhere here, our empirical value, and so we have our empirical value is smaller than our theoretical value. And here you see now the difference between just doing the descriptive analysis and this hypothesis testing, because from a descriptive point of view we would say, well, maybe 72% explanation with our model due to an R squared of 0.72 is quite good. But now unfortunately we see with an error probability of 10% we cannot reject the assumption that there is even no correlation. And now you have to deal within your company. Here we have these parameters of marketing costs, of the number of people, and so, well, is this enough for you really to assume that you have a positive dependence between your parameters and um, um, your data? So this means R squared equals to 0 cannot be rejected for alpha equals 10%. Okay, and the same we are doing now with our example for our single beta values. So here the null hypothesis would be just that there is no dependence, but now with the focus of every single parameter, so that beta is 0, and the alternative hypothesis is just that beta is not 0. So this would be then just the two-sided test. Again, we have to choose an alpha, and now this is our test statistic, and unfortunately also the t-distribution looks a little bit awful. This is looking like this, and oh, this I hadn't explained. This is the so-called gamma function, and the gamma function is the the smooth approximation of the faculty. And remember, this n faculty, this was, let's say, 3 is 1 times 2 times 3. So 1 times 2 times 3 times up to n. And maybe from your introductory course you remember, if you made your experiments with 10 red balls and 10 white balls within a hat and then choosing one, that you have used here this faculty concept. And since we are here now dealing with smooth function, then we need a concept to apply here, and this is then the so-called gamma function. You can look up this in some mathematical or statistical textbook. Well, let's go back to the t-test. Well, we just have to calculate these numbers, and let's step, oh, this is another example. Now let's choose our example which we had. Let's again choose an alpha level of 10%, and we have now a t-distribution depending on 4 within our formula here. We have to set in for our n then 4, and also for this we have in general a table where we then can look up that these critical values for our t-distribution is just given by 2.13, and the t-distribution is still symmetrical, so on the other side we have just minus 2.13. Now let's go to our calculation here. Since we have the fortunate situation that these are our beta values and our standard errors, let's copy this here. So this are then our beta values, and this are the standard values, and our test variable is just given by our estimated values of beta divided by the standard values. So this, since we make a two-sided test, we are just setting to 0. So we have then to calculate just the ratio of our estimated beta value divided by the standard error. This, of course, we can also do here. So minus 2.99 divided by 3.45 for all betas, and this I then want to add here. Oops, copying this with a picture. Putting this down here, so beta hat, this would be then beta hat over SE. And now this was which direction? Beta 4, beta 3, beta 2, beta 1, beta 0. So have to wait until this is saved. So beta 3, beta 2, beta 1, beta 0. And what we then see that, and maybe this is also not that surprising, having performed already the f-test, where we have found that we cannot reject the null hypothesis of an r squared different of an r squared equal to 0, is that here we are always within the interval minus 2.13, 2.13. So this means we cannot, given an error probability of 10%, we cannot reject the assumption that although we find positive and negative values for our betas, that given an error probability of 10%, we cannot reject the hypothesis that still the true values of our betas are 0. And here then you see that, unfortunately, although you find a dependence from a descriptive standpoint between your variables and the sales volume, that for an error probability of 10%, this can be still the case that there your dependence is just 0. So the null hypothesis cannot be rejected for an error probability of 10%. So it is still saving. I have written too much on my slides. Okay, and this would be then just only another example. Again, this would be our beta values, and this you can then do just at home, that you are calculating 10 over 7.5, 1.4 over 0.9, and now for an error probability of 5%, and this you can then look up. For an error probability of 5%, two-sided tests would mean the two areas has to be 2.5%. So this would be then the relevant column for an alpha of 5%. And 8 values, I think we have to assume. Oops. This information I haven't made here. Sorry for this. The n is missing. N should be again just 8, and so our relevant parameter would be then just 4, so it would be then our 2.77. And then you have again to calculate, is our value larger or less than compared to this 2.77. And to be complete here, I gave you also the tables for the F distribution of 95% and 99. So this would be then an alpha of 5% and this would be an alpha of 1%. Okay, that's it for the hypothesis testing. And in your individual term papers, then in general you should care about relaxing these assumptions and other interesting topics. Okay.